University of Oslo. Casey did his PhD at Washington University and graduated in 2018. Then he was a postdoc at the Scripps Institute at San Diego, and in the last year and a half or so is in Oslo. Casey does all sorts of things related to cloud physics, aerosol cloud interactions, cloud feedback. And in the last 2 years or so, he published 2 papers that really make a significant contribution to cloud aerosol interactions, and he managed to narrow down the uncertainty in the effective relative forcing estimations of aerosol cloud interactions, which many of us treat as the holy grail, and that's what we will be hearing about today. Take it away, Casey. Thanks.
Thanks a lot. Yeah, and thanks so much for the opportunity to present. It's really great to be here today virtually. And yeah, I'm going to share some work on satellite-based observational estimates of aerosol indirect effects from marine liquid clouds. And I want to acknowledge my co-authors on this work, Joel Norris, Anna Postner, Truda Sorelmu, Daniel McCoy, Isabel McCoy, and Nick Lutzko, who all contributed through great ideas and pieces of analysis. So the starting point for motivation is that, as I'm sure everyone is very familiar with, the historical aerosol forcing is very uncertain. And to show that, I'm just showing some numbers here of PDFs of historical global effective radiative forcing from IPCC AR6. You can see the greenhouse gas forcing distribution is relatively narrow, so it's relatively well known. The aerosol distribution, relatively wide, it's a large uncertainty, and the aerosol forcing component dominates the uncertainty of the total historical effective radiative forcing. So if we can narrow down this uncertainty, it can help us to interpret climate change over the instrumental record and also understand climate sensitivity to human perturbations better. So that's what we want to try to do, is narrow down that uncertainty. To narrow down the aerosol forcing uncertainty, in our work, we focused on one of the largest components, which is the forcing that arises from the interaction of aerosol pollution with low-level liquid clouds. And this can happen through several mechanisms. First, if there's more aerosol pollution that acts as CCN, if it goes into a liquid cloud, it can cause more numerous but smaller droplets to form. And this increases the optical thickness of the cloud and causes an instantaneous brightening effect, which can act as a forcing on the climate. And then shortly afterwards, the change in cloud droplet number and size can give rise to other changes in the cloud physics that lead to adjustments in the liquid water path or cloud fraction that themselves have other perturbations on the radiation budget. So for example, if the cloud is not precipitating, the more numerous and smaller droplets can lead to stronger entrainment drying, which can lower the liquid water path. And if the clouds are precipitating, the smaller droplets can lead to weaker or suppressed precipitation, which can give rise to different changes in the cloud field properties. So for example, on the bottom, I'm showing a schematic from Danny Rosenfeld's work. The clean conditions are on the left, polluted conditions on the right. And in the clean case, there's relatively small number of large droplets that coalesce to form precipitation easily. In the precipitating clouds, there's cold pools form. They come out of the cloud and collide with each other. And these cold pool dynamics shape the cloud field and make it more horizontally broken up. So that's shown on the left of the diagram. Then as you add more pollution, the droplets get smaller, the precipitation slows down or shuts off completely. You lose the cold pool dynamics, and the result is a more horizontally extensive cloud field with more stratiform cloud detrained out of the convective elements. So this can give rise to an increase in cloud fraction with more pollution. Also, there's potentially changes in the lifetime of the clouds. If they're not precipitating as much, they may last longer. This can also increase the cloud fraction. So there's different ways in which these adjustments can come about. And the quantity we're interested in is the effective radiative forcing from aerosol cloud interaction, or ERF-ACI for short. And it's the perturbation in the top of atmosphere radiation budget that comes about through all of these mechanisms. So in our work, we're really focused entirely on quantification of these forcing components. And what we did is we noticed that in the cloud feedback, there's kind of two different communities: cloud feedback community and aerosol cloud interaction community. And in terms of satellite studies, they were often working towards objectives that were kind of similar, but using different analysis methods oftentimes. And so in our work, we just wanted to try to take some analysis methods that were developed for the cloud feedback literature, adapt them a little bit, and try to apply them to the problem of estimating ERF-ACI. And that's kind of the overarching goal and theme of our work. And so I'll kind of present our estimates in two parts. In the first part, I'll share some estimates of the overall ERF-ACI and the implications for climate sensitivity. And then in part two, I'll share our estimates that break down the ERF-ACI into a Toomey effect component, a liquid water path adjustment component, and a cloud fraction adjustment component to help physically interpret the forcing. Okay, so starting with the first part, we use a method that has been developed in the cloud feedback community called cloud controlling factor analysis. And so the way this works is we start with monthly gridded observations of low cloud properties, which we get from Ceres or MODIS. So I'm just using C to represent a generic low cloud property. And we define low clouds as having a cloud top pressure between the surface and 680 hectopascal. And then we also use monthly gridded reanalysis variables of environmental predictors. And we have a list of 7 predictors, 6 of which are meteorological terms. Those include sea surface temperature, estimated inversion strength, which is an indicator of the inversion strength at the top of the boundary layer. Low level temperature advection. This represents if there's warm air being advected over a cold ocean or vice versa, which can affect the boundary layer stability. We have vertical motion at 700 hectopascal, which can affect the vertical development of low clouds. The relative humidity at 700 hectopascal, which can affect the ability of entrainment to dry out the cloud layer. And also the near surface wind speed, which affects evaporation. So collectively, these 6 terms are kind of considered the standard meteorological drivers, all of the main large-scale meteorological drivers of boundary layer clouds that have been proposed in the literature. And then the last predictor we use is an aerosol term. We use the logarithm of sulfate dry mass concentration at 910 hectopascal. And we chose 910 hectopascal rather than the surface because it's a better indicator of cloud base CCN concentration when the boundary layer is decoupled. And we look at sulfate because it's believed to be the dominant anthropogenic influence on CCN. Okay, so then from these data, we first remove the seasonal cycle and long-term linear trend from all the variables. And then we average the data over a 5-degree latitude by 5-degree longitude grid over the ocean between 55 north and 55 south. And then for each grid box, we use a multilinear regression model where we regress the low cloud anomalies against the anomalies of the 7 cloud controlling factors from that grid box. And what we're really interested in is the relationship between the low cloud properties and the sulfate anomalies, which is highlighted in the bottom equation. But we've included all these meteorological terms so that we can control for them and isolate the relationship between clouds and aerosols without these confounding meteorological factors that could otherwise bias the result. And yeah, so the main advantage of this method is it allows us to estimate aerosol cloud relationships while controlling for all of these meteorological factors. Okay, so now I'll just start by presenting some results. I just wanted to start with showing some maps that show the cloud properties and the relationship to sulfate anomalies, just to check qualitatively the consistency between the conceptual ideas for ACI mechanisms that I started with. So this map here shows the change in cloud droplet effective radius with respect to a local sulfate anomaly, while controlling for all of the meteorological factors. So blue colors here indicate that when there's more sulfate aerosol, there's smaller cloud droplets, which is consistent with the Toomey effect. We can see this is widespread across the global ocean. This one now shows the change in liquid water path with respect to a change in local sulfate concentration. Red colors here indicate that lower liquid water path occurs when there's larger sulfate aerosol concentration. And we see the typical subtropical stratocumulus areas popping up here. So this could be, or this is consistent with perhaps enhanced entrainment drying, lowering the liquid water path when there's more sulfate aerosol in the stratocumulus regions. This map now shows the change in cloud fraction with respect to a local sulfate anomaly. Blue colors here indicate that when there's more sulfate aerosol, there's a larger liquid cloud fraction. So this could be consistent with a precipitation suppression effect or a lifetime change as well. And then a common point of confusion, for me at least, when I started looking at this, that I want to go over now is the fact that the liquid water path decreases when there's more aerosol in the subtropical stratocumulus regions, but the cloud fraction increases. Those would seem to be contradictory to each other. And to explain that, I just want to put up the conceptual diagram that I showed a minute ago. The key to understanding this, I think, is to remember that the liquid water path is computed averaging over the cloud-covered portions of the domain. So on this diagram, there's more aerosol moving to the right. It's pretty clear to see that there's a larger cloud fraction as the aerosol increases. But if you consider that the liquid water path is averaged only over the cloud-covered portion of the domain, you can see on the left, these thick, rainy clouds with high liquid water path make up a large proportion of the cloud-covered area when it's clean. And then when it's polluted on the right, these thinner, low liquid water path stratiform cloud elements make up a larger proportion of the cloud-covered area when it's polluted. So this explains how the cloud fraction can increase, but the liquid water path averaged over the cloudy areas can decrease as there's more sulfate aerosol. Okay, and then finally the last one, this shows the shortwave low cloud radiative effect anomaly with respect to a local sulfate anomaly. And blue colors here indicate that when there's more sulfate aerosol, the low clouds are reflecting more shortwave radiation to space. So an overall would suggest a negative forcing as expected. Okay, so these cloud radiative effect aerosol relationships that I just showed, these can serve as a foundation on which we can make forcing estimates. But before we do that, we wanted to actually validate the method based on its ability to predict cloud changes when we know there's a change in aerosol sources that's driving the cloud changes. And so the reason we want to do this validation is because when we're looking at natural variability in the observations, it's not always clear if the aerosols are causing a change in the clouds, or the clouds are causing a change in the aerosols, or both are happening. There's a lot of mechanisms in the literature that have been proposed that suggesting the causality could go in both directions. And for forcing estimates, we really want to know the causality from aerosol causing cloud. We want to know in that direction. So yeah, we wanted to do some validation tests to make sure that this method is fit for purpose for making forcing estimates. So to do the validation, we looked at a few cases where there's a known change in sulfur dioxide emissions. So we know there's a change in aerosol emissions, and this change is giving rise to a change in clouds. And we want to see then if our method can predict that cloud response. So the first test case we looked at is in Eastern North America. And the study region is outlined in the box in the map in the bottom left corner. So this is downwind of the Eastern United States over the ocean. And what's plotted in the time series on the left is the sulfate anomaly over time, averaged over the box, where the seasonal cycle has been removed, but the long-term trend has not been removed. So you can see a declining trend over time in the sulfate aerosol concentration. This is associated with stronger emissions regulations over time in the United States to reduce air pollution. So this is an anthropogenic signal. And furthermore, we removed the trend prior to doing all our regression analysis. So the information from this trend is not used to do our cloud controlling factor analysis. So it's kind of like an out of sample information. So then we wanted to ask the question, if we input the trends in all the cloud controlling factors into our regression model, can we predict the trend in cloud radiative effects in this area? And so the result of that calculation is shown on the right. What's plotted, delta R short W, is the change in shortwave low cloud radiative effect in the study region, averaged over the first 8 years, the first half of the record, the second half of the record minus the first half of the record. So it's basically the decadal change or the decadal trend in low cloud shortwave radiative effect. And the black line here is the observed value. And the first data point, which says total, is the predicted value from the regression model, which agrees quite well with the observations. And then we can further break that down into a sulfate-driven component, which is shown in the middle data point, and then a meteorology-driven component, which is shown on the rightmost data point. We found that those contribute comparable amounts to the shortwave cloud radiative effects decadal change in this area. We've also done this analysis downwind of Eastern Asia and found similar results, but the trend is the decadal trend in cloud radiative effects and sulfate emissions is smaller in the region we looked at. So it's kind of a weaker test, but it still worked out. And then another test we looked at is we looked at a volcanic eruption of Kilauea volcano in Hawaii. That's what's shown on the bottom. So now we're looking in the Pacific Ocean. You can see in the map in the bottom left corner, there's a dot for the volcano and then a box downwind of the dot, and that's where we're looking at examining data. And so the time series now on the left shows sulfate anomalies over time, where now both the seasonal cycle and long-term trend have been removed. And you can see two spikes in the time series that are highlighted with black bars. These correspond to volcanic eruptions of the effusive volcanic eruptions of the Kilauea volcano. And so what we did is we removed data from these eruption periods, then repeated the cloud controlling factor analysis with the remaining data, and then used the regression model to predict the cloud radiative effect anomalies during the eruption periods, when we know there's a big anomaly of sulfate. And the result of that calculation is shown on the bottom right. So again, the black bar is the observed value of shortwave cloud radiative effect anomalies during the eruption period. The total prediction from the regression model agrees pretty well with, very well, I would say, with the observations. And in this case, we see that the sulfate contribution to the cloud radiative effect is dominating the signal, as is expected for a volcanic eruption. So these kind of out of sample tests give us some confidence that the method can make accurate predictions of ERF ACI. Yeah. Okay. So now we wanted to take our method and make an estimate of ERF ACI. To do this, we take our regression coefficients relating the net low cloud radiative effect to local sulfate anomalies that we get from the statistical analysis I just showed. And then we multiply by the change in sulfate concentration between 1850 and 2014, which we get from CMIP6 historical simulations. And we averaged over the ocean domain between 55 north and 55 south. And then finally, we had to do a little bit of extrapolation to go from a global ocean average to a true global average. And we do that by introducing a scalar we call gamma, which is in blue. And this is the ratio of the global average ERF ACI to the ocean average ERF ACI that we get from CMIP6 climate models. So we're using the models to extrapolate. The gamma parameter is quite close to 1 in the multi-model mean, but it has some intermodal spread. So basically it doesn't change the forcing estimate very much, but it inflates the uncertainty. And yeah, so we have estimates of the delta log 10S term, the sulfate change, which is shown in red from 20 CMIP6 models, estimates of gamma from 20 CMIP6 models, and we constructed 95% confidence intervals by creating the interval that spans 19 of the models and excludes one model for both of these terms. And then we can kind of put it all together and get an estimate of global ERF ACI. So this is the result of that calculation. I'm also comparing to some recent community assessments just for reference. So the top is the estimate from a recent community assessment from the WCRP, World Climate Research Program. That was led by Bellowen et al. In 2020. The middle bar is the IPCC AR6 estimate for observational-based evidence. And the bottom is our estimate. All of these are for liquid cloud, ERF ACI from liquid clouds. And so our estimate falls within the range of the previous community assessments, but has a narrower uncertainty range, and most importantly, the upper bound of our estimate is quite a bit more negative than what has been argued before in these community assessments. So in other words, according to our analysis, the possibility of a near zero ERF ACI is being ruled out, whereas it's not being ruled out by the previous evidence. So then we wanted to ask, what implications does this have for climate sensitivity? If ERF ACI is relatively strong, it means all of the warming that has happened over the historical period happened even though aerosol cooling has canceled out a significant fraction of the warming effect of greenhouse gases. So if that's true, it must mean that the climate sensitivity to greenhouse gas changes is relatively large compared to kind of what had been estimated before. So to quantify this, we used a framework developed by Sherwood et al. 2020. It's a Bayesian analysis that combines multiple lines of evidence from the historical record, from feedback process understanding, and from paleoclimate evidence to make an estimate of the ECS, equilibrium climate sensitivity. This is the long-term warming that would occur from a doubling of CO2 after the system has reached equilibrium again. So again, I'm comparing our result on the bottom to IPCC AR6 and the Sherwood et al. Assessment on the top. And when we, so what we did is we reran the Sherwood et al. Code, but we just replaced their estimate of ERF ACI with our new estimate. And when we did that, we got a higher ECS, median value shift by about half a degree. So our results are suggesting that ECS is higher than perhaps higher than previously thought. So the main takeaways of this are our analysis supports a smaller uncertainty for ERF ACI from liquid clouds and therefore a larger ECS.
Maybe could I ask a quick question on this last one? So do you know why your uncertainty gets bigger?
Yeah, that's a good question. I think it's because there's a nonlinear relationship between ECS forcing and feedback. So for example, Gerard Rowe has some papers showing that if you shift the central estimate of forcing or feedback, but keep the uncertainties the same, that can give rise to an inflated uncertainty in ECS because they're all nonlinearly related.
Okay, great, thanks.
Yeah. Actually, maybe I can, if there's any other questions, I'd be happy to answer them. Otherwise, I can go to part 2. Yeah, okay.
Yes, I would like to ask a question. This is Danny Rosenfeld. You used for your susceptibility study grids of 5 degrees by 5 degrees for 1 month. This is smoothing away much of the real variability, and especially smooths away the very clean situations which possess the greatest sensitivity. My graduate student, Carl Young, did it at 1 by 1 degree on a daily scale and got even much larger susceptibility. And if we plug it in your results, the ECS should be even much higher and the ERF ACI should be even more negative.
Yeah, that's a good point. In the cloud controlling factor literature that we based our work on, they chose a scale of 5 degree by 5 degree in 1 month because it's been argued that one needs to choose a scale that's sufficiently large so that the boundary layer clouds can come into quasi-equilibrium with their environment. And if you get too small, then you may be violating that quasi-equilibrium assumption. I'm not sure exactly where that cutoff would be, where you're kind of too small scale, too large scale, or too small of a scale. but that was the reason we chose that particular scale. But it would be, yeah, it would be. I'll have to look for your study, and I think it would be quite nice to check out.
We have been looking into volcanic eruptions as well, and we are finding that it still holds there.
Okay, yeah, good.
So therefore, I think that there is uncertainty in your uncertainty, and so to speak, and the question of scale is really an important one.
Okay, yeah, I'll keep an eye out for your paper, and
it's now being written. I mean, we published already a series of papers. You may look at previous papers of Cao Yang with me as a co-author.
Okay,
also
yeah.
doing the trends in the northwest Atlantic with cloud cover and components, very parallel ways.
Okay, yeah, thanks a lot. I'll keep an eye out for that.
Thanks.
Okay, so now I want to shift to the second part of the talk, and the goal of this part is to, instead of making just one estimate for ERF-ACI, we want to break it down into components, into the Toomey effect piece, the liquid water path adjustment, and the cloud fraction adjustment. And the reason for doing this is that first of all, it helps us to interpret on physical grounds what mechanisms are most important to the ERF-ACI, where it's a step in the direction towards understanding the mechanisms. And secondly, it helps us to kind of compare our results to other evidence that's been published before, because many studies have been focusing on the Toomey effect piece, the liquid water path adjustment piece, and the cloud fraction adjustment piece. So if we can break down our numbers into these pieces, then we can compare to other studies, which is of course helpful for framing the results in the context of what's already published. A note of caution is that in the first part, we estimated the net ERF-ACI for low-level clouds, defined as clouds with a top between the surface and 680 hectopascal. And in the second part, we're estimating the shortwave component of the ERF-ACI for liquid top clouds, which are a slightly different subset of the population than low-level clouds. So the numbers are not exactly comparable, and unfortunately, we couldn't avoid this discrepancy because it arises from the kind of formatting of the monthly MODIS data that we use. But with that being said, the estimates from part 2 for the overall shortwave ERF-ACI are approximately comparable to the estimates from part 1. Okay, so yeah, just a little bit of background for how we did this. I want to introduce an analysis method called cloud radiative kernels that are really commonly used in the cloud feedback literature. So what's done in this body of literature is the data they use is a joint histogram representing the cloud fraction partitioned by the cloud top pressure of the highest cloud in the scene and the total column optical thickness. So just an example of one such histogram is shown on the left. These histograms are typically available as a function of latitude, longitude, and month. Then there's something called a cloud radiative kernel, which represents the change in top of atmosphere shortwave flux that would occur if the cloud fraction changed by 1% with everything else held fixed. So this represents the radiative impact, and it's done for each bin of the histogram. So represents the radiative impact of cloud fraction changes for each bin of the histogram. And then from there, one can compute the cloud-induced radiative flux anomaly at the top of the atmosphere, R prime, by multiplying cloud fraction anomalies C prime from each bin of the histogram by the kernel, and then summing over all of the histogram bins. And this is typically done for cloud feedback. So C prime in that case would be the change in clouds between a 2 times CO2 or 4 times CO2 simulation and a control simulation. And there are also methods that they have developed to kind of break down the cloud change into a shift along the vertical dimension of the histogram, a shift along the horizontal dimension of the histogram, and a change in the total cloud amount while holding the proportion of cloud fraction in each bin of the histogram fixed. And so when they do all that analysis, those are interpreted as the cloud altitude component of the feedback, the cloud optical thickness component of the feedback, and a cloud amount component of the feedback. And I know I'm going over this very, very quickly, but yeah, just the main point is that this is a very widely used technique in the feedback literature. And in our work, we wanted to try to bring this into the ACI literature, and to do that, we tried to keep things as similar as possible, but we just changed the dimensions of the joint histogram. So now our histogram comes from MODIS. It's for liquid top cloud fraction instead of all clouds. And the dimensions of the histogram, which is shown on the left, are liquid water path and cloud droplet effective radius. And then we computed a radiative kernel for this using the same method as the feedback community uses, but just with different dimensions, with a radiative transfer model. And then we can use the same mathematical techniques that they've developed in the feedback community, but when they're applied to these histograms and kernels, what they allow us to do is break down monthly anomalies of liquid cloud radiative effects into a component driven solely by cloud droplet effective radius anomalies, a component driven by liquid water path anomalies, and a component driven by liquid cloud fraction anomalies, each computed with the others held fixed, the other properties held fixed. And then we just do the same cloud controlling factor analysis as before, but performed on each of the components of the cloud radiative effect anomalies. And then the result we get is one term that represents a Toomey effect, one term that represents liquid water path adjustment, and one term that represents cloud fraction adjustment. So then from that analysis, we can make maps like this, showing the Toomey effect, liquid water path adjustment, and cloud fraction adjustment. Now the units are in watts per meter squared per change in local sulfate concentration, or logarithm of local sulfate concentration. And so these can be interpreted as the Toomey effect and adjustments that would occur if the sulfate were increased by a factor of 2.7 at every location over the ocean. And so now we can start to see the radiative impacts of the adjustments and the Toomey effect. And what we find from these is that the cloud fraction adjustment seems to be quite important. As a sensitivity test, we also did the analysis with MODIS cloud droplet number concentration as the proxy for aerosol, instead of sulfate from MERA2. And we found similar spatial patterns and relative magnitudes of the terms when we use this alternative and independent CCN proxy. So this gives us some confidence that the results are robust to the choice of CCN aerosol proxy. Okay, so then the last thing we can do with this is make estimates of the shortwave ERF ACI from each component averaged over the ocean between 55 north and 55 south to see the relative importance of the Toomey effect in the adjustments. And for context, I'm showing our study, which is in a darker color, and assessment from Bellowin et al. 2020. This is the WCRP assessment from before. And then estimates from 14 GCMs that came from CMET5 and Aerocom models that were computed by Ed Griesbert. And so for the Toomey effect, we find that our best estimate agrees quite well with the published literature, but with a smaller uncertainty range. We found evidence for a positive liquid water path adjustment and a negative cloud fraction adjustment. But a caveat with these is that if one makes different reasonable choices about how you could filter partly cloud covered pixels, then the numbers change a little bit. So these really need to be interpreted with caution, I think. But then when we compute the total adjustment, by which I mean the sum of the liquid water path and cloud fraction adjustment together, the sensitivity to partly cloudy pixel filtering is no longer an issue. It's robust across different filtering choices. And so this is, I think, our robust result about adjustments. And this is where our work differs most from the published literature. You can see the GCM and Bellowin et al. Estimates have about a 50% probability that the total adjustment could be is an order of magnitude smaller than the Toomey effect or positive. But according to our results, that such smaller positive values are not plausible, according to our estimates. And instead, the total adjustment is comparable to the Toomey effect. And this is ultimately what gives rise to the relatively strong ERF ACI that we estimated before. So the main take-home point from this analysis is that our work supports a Toomey effect that's consistent with what's been published, but a relatively strong cloud adjustment. And then the combination of those two things leads to a relatively strong overall ERF ACI. And yeah, I think that's the end of my talk now. I'll just summarize briefly. We studied effective radiative forcing from aerosol cloud interactions from liquid clouds over the global ocean using satellite data and taking analysis methods that had been developed in the cloud feedback community, adapting them and applying them to that problem. And our analysis supports a smaller uncertainty for ERF ACI, a relatively strong cloud adjustment, and a larger ECS relative to what has been published in recent community assessments. And we have a couple of papers. If you're interested in more details, they're listed on the bottom, and also my email is on the bottom as well. So please feel free to reach out if you have any other questions. And yeah, I'd be happy to take any questions now. And thanks a lot for being here today.
Yeah.
Thank you very much, Casey. It was very interesting. Yeah, Danny, go ahead.
Yes, we've gone through all these exercises, and we get even larger susceptibilities. We first published it in my science paper in 2019, I think, the one that you're quoting, and there we wrote that it might be too much cooling. That will be impossible if there was not some missing balancing warming from the deep convective clouds. And now we are looking also into this question, and we find some missing warming that we are still working on publishing. You know, when you try to publish new stuff, you have a lot of resistance. But don't be discouraged and not be deterred by showing non-traditional large negative forcings.
Yeah, thanks a lot, Danny. That's also been something I'm really interested in and hoping to look into as well, is the forcing from deep convective clouds, because like you said, there just isn't an estimate yet. And so I think that's the important next step to make.
Yeah, we have some preliminary results that show warming, and that is simply because people have been doing the very basic mistake for cloud, for deep cloud radiative effect, as the reference is clear sky. But if you eliminate the deep clouds, you are left with low clouds. and that should be the reference. When you do that, the whole calculation changes.
Okay. Yeah, really interesting.
That is a very simple implied assumption, which is typically the causes for most failures.
Okay. Yeah, I'll definitely be really interested to see that.
If we have questions from students, that would be great. Otherwise, in the meantime, I'll ask a question. I think it's really cool that you're using methods from cloud feedback, from the cloud feedback community and the cloud controlling factor and the kernels. I think it would be really cool also. So basically, it's all done locally, right? The effect of local aerosols on clouds. Do you think it would be possible to use also something like grain functions or something like that to look on remote effects of aerosols on clouds from observations?
Yeah, that's a really, really interesting question. I was actually reading your paper on remote impacts recently, and I was also thinking the same thing. Like, it's an important limitation that we're just looking at local impacts. But the challenge, I think, is how do we estimate the change in meteorological cloud controlling factors that arises from the local change in aerosol cloud radiative effects. There's like a one more step that we need to take, which is, okay, you have some aerosol, it locally changes the clouds, that causes a local radiative forcing that can give rise to a change in circulation or other meteorological factors, which can then give rise to an additional forcing. How do we know what that's change in meteorology and should be without a model? I'm not totally sure yet. So that's why I'm kind of getting stuck there with the observations. Yeah.
Yeah. I mean, it won't give us a result in terms of maybe the average effective relative forcing, but one thing we are looking at, I have a student, she's here, I think, Neta, looking on Lagrangian trajectories and looking on the evolution, you know, when you move downwind from subtropical to tropical regions, and how, you know, perturbation in the subtropics affect cloud downwind and so on. That
By the way, Guy, what you do here is actually when you have more cooling in the subtropics, you have more or deeper clouds in the ITCZ, which give more warming that perhaps compensate some of the additional cooling. That's interesting.
Yeah. Okay. Any other questions beside Daniel and me? Which I'm sure we can go on.
Well, I have a question. First of all, sorry, I'm hearing an echo. It was very interesting. I just wanted to ask, why did you choose or need to do the analysis of the first part, particularly over the oceans, not land? And also, why is it expected that a constant factor can be used for, you know, going from the ocean average to the global average?
Yeah, we did the ocean study over the ocean simply because the cloud controlling factor framework hasn't really been developed fully over land yet. I think one would need to use a different set of controlling factors over land. For example, soil moisture. There's other possible variables one would need to consider, and that just simply hasn't been fully done yet. So that's why we looked at the ocean. Yeah, I think the second question was, is it reasonable to extrapolate from ocean average to global average? And for that, I would say, at least in the CMIP6 models and all 20 of them that we have, we made a scatter plot of global average versus ocean average ERF ACI for all the models, and they were all quite close to the 1-to-1 line. So So at least according to the models, it's, I think, reasonable to do, and it's kind of the best we can do at this point. But I think that if the cloud controlling factor method kind of gets more developed and more mature for land-based studies, then that could be definitely a nice addition to kind of do that separately and then merge it with the ocean analysis, and then avoid to make assumptions with
I have additional answer for that. The cloud above a certain level of aerosols, the cloud response saturates, and that level is been exceeded or very close over most of the land.
Okay. Yeah, that's a good point.
Interesting. Yeah, thank you.
Okay, cool. Thank you very much, Casey. It was really interesting. And thank you all for coming. We'll see you all next week.
Thanks, Casey.
Right,
Thank you.
everyone.
Thank you.
Thank you.
Bye, everyone.
Thanks. Bye-bye.